Welcome to the Wind Sustainability Series. This is the episode number 5, Climb. In this episode, we will review the current initiatives and operational recommendations that will help to reduce fuel consumption and CO2 emissions during the takeoff and climb phases. The first constraint that can affect the consumption during the takeoff and climb phases is the trajectory. The air traffic management has a key role to play when it comes to maintaining the deviations from the optimum trajectory as small as possible. For example, at airports with intense traffic, ATM can assist with better climb profile, for instance via the reduction of level off, or the application of optimized EP5 procedures for departures. As you are aware, in terms of aircraft operations, an accurate computerized flight plan is one of the most important ways of reducing fuel burn and CO2 emissions. However, the nature of some of the parameters can result in some lack of accuracy. In order to make the best from the CFP, it must be accurate and in line with the aircraft performance. It is then important to continuously monitor the aircraft performance to keep the CFP prediction as close as possible to the real aircraft performance. For a given departure, the lowest flap setting will produce the least drag and so give the lowest fuel burn. However, other priorities such as maximizing takeoff weight, the takeoff speeds, or ground noise, for instance, may require higher flap settings. The most appropriate flap setting should then be selected for each departure, rather than systematic use of the same configuration. In this table, you can see the fuel saving and CO2 emission reduction done with a conf 1+F instead of conf 3 set for takeoff. Keep in mind that the right balance between performance, noise, and fuel consumption should be found during the selection of the takeoff configuration. The takeoff thrust reduction or reduced thrust takeoff, flex takeoff or flexible takeoff is a technique to optimize the thrust used at takeoff based on the aircraft weight, the runway, and the ambient conditions. The advantage of operating the engines at a lower thrust compared with fuel power is an extension in engine life and reduced maintenance costs. The flexible takeoff is the recommended method for takeoff at reduced thrust on dry and wet runways. It must be noted that the highest flex temperature will usually be obtained at the lowest flap setting. It is also important to have in mind that the use of flex takeoff increases the fuel consumption compared with the toga thrust. Once again, a right compromise between maintenance costs and reduction of fuel consumption and CO2 emissions needs to be found depending on your operational constraints. Now, a few words about derated climb. The engine life may also be extended by operating the engines at less than the maximum climb thrust. Climb performance is reduced when using the derated climb thrust, but the ceiling is not affected. The derated climb increases the time and distance to the initial cruise altitude. Furthermore, the use of derated climb also slightly increases the global fuel consumption at a specific cruise altitude. The flight crew can insert climb wind values for different flight levels during the flight planning initialization. To obtain the base predictions, the flight crew must enter the wind for the various flight phases. Then, during climb, the FMS takes into account the forecast wind to compute the fuel and time predictions and also the ECOM speed Mach targets. The more accurate the wind data is, the more efficient the climb will be. For more information about the forecast wind profile computed by the FMS for the climb waypoints, you may also refer to the flight crew operating manual. By default, the FMS flight plan takes into account the 250 knot speed limitation below 10,000 feet. If the ETC permits, the flight crew can remove this limitation in order to accelerate to the optimum econ speed and save cost and fuel, and then reduce fuel consumption and CO2 emissions. If the conditions and regulations permit, the flight crew should reduce the altitude for both the thrust reduction altitude and the acceleration altitude. Indeed, a low acceleration altitude minimizes fuel burn as it enables an earlier retraction of the flaps and slats and achieving a more efficient aerodynamic configuration with minimum drag sooner. Note that by regulations and design, the lowest authorized acceleration altitude is 400 feet. This table displays some examples of fuel savings and reduction of CO2 emissions for an acceleration altitude at 800 feet instead of 1,500 feet. As a summary, you can find in this slide an example of the theoretical takeoff climb profile that would have the best results in terms of performance and fuel consumption. To obtain the best efficiency and reach the top of climb earlier, we recommend to first adapt the departure trajectory, use optimized takeoff flaps configuration, reduce the thrust reduction altitude and acceleration altitude as much as possible, and finally, request removal of the climb speed limit and follow econ speed. Thank you for watching this episode of the Wind Sustainability series. Stay tuned for more on how to reduce fuel consumption and CO2 emissions during the other phases of the flight.